start now. Right before the break, we obtained the expression for the work in terms of rho and v, right? So hey, Hope, it's in the recording right now. Okay, so please be quiet. So hey, be quiet. It's now recording. And so before the break, we have the expression of the work as a function of the charge density rho and the potential v here. And now what we want to do is to eliminate the expression for the v in terms of e, because the gradient of vector, the gradient of this scalar potential simply gives us the negative electric field, right? So now we can also express the rho, or this charge density, in terms of the electric field using the divergence of the electric field. So really we can eliminate both terms in favor of the electric field. And what that gives is so first step here, I did the eliminates the charge in favor of the del dot E. And now what I can do next is to use the integration by part. So here del dot E was something that we want to preserve, because we want the electric field be there, and we want to eliminate the vector v, sorry, the scalar v, or the scalar potential. And the integration by parts actually can do this, right? So instead of applying a gradient operator here, we can remove this determinant. We can move this divergent to a gradient operator on this scalar v. Now if we write this out, we have two terms. One is this gradient of v we just talked about. But remember that if we do the integration by parts, we added another term, and that is related to the edge of this integration. And this edge of a volume is a surface. And here, this surface, whether this surface located is something that we need to discuss. And here, since we are interested in this potential energy of this electric field in all the space, right? So really we are interested in an infinitely large volume, and this integral edge should be the integration at infinity. And we also define our reference point of the potential energy V here. The V at infinity gives us 0, right? So in the end, this means that this term goes to 0. So that's the beauty of the integration by part. And oftentimes, the second term is 0, and what we need to do is only the first term. And now, this gradient of V simply gives us minus E. So the work is really the first term only, and the first term is the E squared. So you can see that this expression is actually extremely simple in the end, and the work is actually proportional to the electric field squared, and that is actually something that's quite unexpected. And now here, the example, we can try to calculate the energy of this E field in two ways. One is to calculate the energy in terms of rho V, and another is simply calculating the energy in terms of E squared. And this example is the example that's what we just went through, and so it's uniformly charged spherical shell, and we already worked out the potential, and we worked out the electric field. So you simply plug everything in, and I'll just sketch the result. So if we do this using the method 1, this volume integral is really a surface integral because we only have the surface charge here, and now you can simply plug in everything, integrating over theta and integrating over phi, and the charge is simply q over 4 pi r squared, and the v is what's inside, so it's and the volume element is r squared sine theta d phi d theta. And if you do this integration, it gives you 8 pi epsilon naught q squared over r. And similarly, for the second method, we integrating the E field across all the surface. Here, we need to pay attention that because the surface charge is at the r position, so there is no integration along this r direction, right? And here, however, for the E field, we really need to integrate both from the inside of the shell and to the outside of the shell. And so this gives two terms. And the first term inside the shell is 0 because the electric field is 0, and so W inside is, and W outside can be integrating over the r direction, the theta direction, the phi direction. I'm not going to write this down, but in the end, you see that the two actually give the exact same result. Then you may start to wonder that according to the first expression, the energy seems to be stored on the surface charge itself, right? And according to the second expression, the energy seems to be stored over the entire space and in the electric field. And which one is really correct? So that's not an easy question actually to answer. And the answer should be that the energy really is stored in the field itself and not on the charge. But for us right now, the two understandings are equivalent to each other, and you can think of this storing the charge, and it's simply a bookkeeping system for now. In the later part, you might be appreciate why the energy is really stored in the electric field itself instead of the charge. But we won't talk about this until later. And I also want to make some comments about this potential. And so the first one is that if you integrate out the potential of a point charge, that actually gives you infinite. So you can try to do that. So the electric field square d tau, where the electric field itself is 1 over r squared, and 1 over r squared squared is 1 over r to the 4th. And if you integrate over the r squared sine theta dr d theta d phi, that gives you integration of 1 over r dr, and this integral will actually diverge if we integrate over all the space. So what does this mean? That a point charge potential diverge? It means that it's actually quite hard or actually impossible to fabricate a point charge, right? Because this is what we are trying to do. You are trying to squeeze a continuous distribution of, say, a Gaussian function, that is a three-dimensional Gaussian, into a really sharp peak, right? And in this process, you actually need to pay infinite amount of work to fabricate this delta function. So this delta function is really not quite physical, but is a mathematical powerful tool for us to understand. And if we don't care about the details of the point charge, and so oftentimes in reality we never see point charge, and it's always tiny distribution of charge. But if we really describe the charge distribution as a very small peak of a Gaussian, then it really complicates the stuff and brings unnecessary trouble into the problem. The delta function is only a very simple model for us to use, and this model has limitations, but can be handy or useful in many situations, as long as we know the caveat of this delta potential or this point charge. Now, the second point that I want to mention is that if you look at the expression for the potentials stored in the electric field, this expression is E squared, which means E squared is a positive number, and integrating over all space again is give us a positive number, right? However, if you look at the expression over here, it says that the charge is all. If we go back really to the point charge expression, here if we flip the charge from all positive to all negative, then this expression suggests that this W, this potential energy stored in this field or in the charges, can either be positive or negative, right? So these two seem to be conflicting each other, but in reality, what's happening is that because of the first comment here, the point charge energy is actually divergent. So it doesn't make sense, or if you're comparing the infinite number to another infinite number. So this means that whenever we are talking about the energy field for a point charge distribution, then maybe we have to stick with this first expression, the expression involving Q and V, instead of using the E squared, even though the total energy stored in this point charge is positive, which is positive infinity, but that doesn't give us quite much information, right? Maybe sometimes we want to figure out what's the potential energy difference if we move the point charge configuration slightly. And if we are always saying that, it's infinite minus it's infinity minus infinity, then there's nothing that we learn. And so this QV expression might be sometimes useful, but what's underneath physical, it should be E squared. And now, if we look at this E squared expressions and checks the superposition principle, and we add two E fields together, and that immediately gives the E1 plus E2 squared which is not E1 squared plus E2 squared. Really, there is an additional term that is a cross term, which is E1 vector dot E2 vector. And this term is something that you need to pay attention to. So this means that if you double the E field, say in a capacitor, the work is not simply double. You need to multiply by a factor of 4. Now, next we want to discuss the last topic in this chapter 2, which is conductors. So for conductors, we are very familiar that typically for material there are two kinds that we are interested in this electrostatics. One kind is the insulator, which is glass, rubber, or many other materials. We will discuss this later in chapter 4. And right now we will discuss conductors, and which could be metals which have free electrons, or if you add salt to the water, there can be ions in the water, and these ions can move freely. So for conductors, there are free charge in the system, and for simplicity, we want to look at the ideal conductors, which means unlimited number of free electrons. So for an ideal conductor, there are really unique properties. So which means, say that if we have a conductor here, and outside there is an electric field, and because the electrons in the conductor can move, right? So the charge will be moved to the surface, trying to, and what this in the end it does is it moves positive charge to this side and the negative charge to the other side, and itself will counteract this electric field, and in the end the charge inside won't move until it reaches the equilibrium where the internal electric field is 0 and exactly cancels the electric field outside. And you can calculate the charge density inside, that it should be exactly 0, because the E field is 0, and delta E is proportional to density inside. And then this means that if there are net charge, then it must be on the surface. And what's next is this means that if we calculate the potential inside this conductor, the potential must be the integration of the E field, right? And this gives us a constant because the E field inside the potential is 0. And finally, one particular unique property of the conductor is that the E field must be perpendicular to the surface. So no matter how strange this conductor shape looks like, the E field must be exactly perpendicular to the surface. So can you try to prove that? So the E field inside is 0, and if we earlier in the lecture we actually already derived that the E field outside minus the E field inside, it should really be the surface charge divided by epsilon naught n hat. I'm not sure if I missed a minus sign or not, but because the E inside is 0, right? Then this means that E outside must be perpendicular to the surface. So no matter how strange this shape, it's always perpendicular to the conductor. And now let's try to take a look at what happens if we bring a charge close to a conductor. So here, suppose that we have a conductor on over here, and we add additional point charge. Then the point charge has its own electric field, and naively thinking, it will attract the negative charge to the left side, and then what this does is that the positive charge must accumulate on the other side, because the positive charge repels the positive charge over here, and the net charge of this on the surface must be 0. So this means that in this particular case, the conductor should actually be attracted to this point charge, and we will see later that in general the conductor will be attracted by the charges. But here, let's take another example. So this example is to suppose that we want to cut a hole in this three-dimensional conductor, and in this hollow region we put another point charge inside. And what this does is, so first the electric field at the conductor must be exactly 0, right? So if we invoke Gauss' law and enclose this region, we can then find that there must be negative Q charge. Sorry, we should invoke the Gauss' law outside first, and then if we do that, if we enclose Gauss' law outside first, then we can know that the total charge inside must be Q, and because if we look at this, if we do a Gauss' law again in the inside direction, then the inside should be giving let me see, I'm confused. So if you do a Gauss' law integration inside the surface, because the surface because the surface that's enclosing the surface, the electric field is 0, then this means that the total charge inside this volume should be 0, right? So this means that on this edge there should be minus Q of the charge that's countering the charge Q inside, and that gives that this minus Q should be balanced by the plus Q charge on the outer surface, right? Then now the magic is that if we do a Gaussian integration, that's a spherical Gaussian, and this integration, what this does is that if we calculate the electric field outside, the electric field must not depend on how this hollow looks like. What it depends is the total charge inside, and that is because outside here at the surface, all the charge should be uniformly distributed, and this uniformly distributed charge behaves as if a single point charge right exactly at this center. So this is the idea of Faraday's cage, and this is the screening effect, and if you do the opposite, and if you put the source outside, then it will this electric field will shield the outside electric field from penetrating the surface. And so if you look at this problem, what's really unknown is in the hollow regime. So outside this conductor, it's behaved like a point charge, and inside the conductor, the electric field is 0. And what's inside the hollow region can be complicated, and this is something that we can try to calculate in the next chapter. That is, given a conductor outside, and there could be some charge inside, and what could be the solution to this problem, and could you find out the electric field exactly inside? So that's in chapter 3. Now next I want to go back to our problem earlier here, is that so oh sorry. So we see that this conductor might be attracted by this point charge, right? Because if you see that here the negative charge is closer to this positive charge, so 1 over, if you calculate this, 1 over r squared negative must be larger than the 1 over r squared positive charge, like the positive charge is from here. This means that the force exerted by this point charge must be an attractive one, and it will attract the conductor to the charge. And how do you calculate this force? Well, what I claim here is that the surface charge can really be calculated using the F should be proportional to the surface charge times the electric field, right? But what exactly is this electric field? On a surface, there can be electric field outside and the electric field inside, right? And shall we use the electric field outside to represent the charge, the force field, or use the inside electric field? Well, the answer is actually we should actually use the average of the two. I can try to give you an explanation for that. The reason is that say that we simplify the problem, and this is a surface with surface charge sigma, and we are interested in the force experienced by this small region, right? And a particle can this region cannot exert a force on itself. So when we are calculating the force, we really need to exclude the contribution from this one, and so the electric field might be the electric field of the black region plus the electric field of the white region, and what we want to include is E average is the E white region, and we already know what the E black should be, because that's the E field due to this small tiny patch, and we can use Gauss' law to calculate the electric field. So for a surface charge sigma, there is must be electric field pointing up and pointing down, and that must be proportional to the surface charge, and I'm not sure if there is a 2 or not, but it should be 1 plus sign above and 1 minus sign below, and then this the electric field due to all other regions is really the same, whether you are above or you are below. So this is above. So if we do an average of the E field above and the E field below, what you get is actually the E field from the white region, that's excluding the central patch. So here, this average is a smart way is to excluding the self force. Okay, now next, this discussion is force on a general surface charge, but what we have here is a conductor, right? And for a conductor, the E field must be proportional to surface charge divided by epsilon naught, and that is you can simply get that by using Gauss' law and setting the E field inside the conductor to be 0. And that readily gives us the force a conductor field that if we simply plug this E field inside the expression here, and that gives us sigma times E divided by 2, and which is sigma square divided by 2 epsilon naught. And if you express the sigma back in terms of E field, that is epsilon naught E square over 2. And here this force is a little f, which means this is the force per area. And which means that this is really the pressure. So this pressure is proportional to the E field square of a conductor, and you may be able to apply this to one of the homework problems, but you don't have to. Okay, so next. Let's look at the final chapter, that is capacitor. So capacitor is really bringing two metals close together, and we charge one metal by Q and charge another metal by minus Q. So for an ideal parallel capacitor, then there will be an E field only within this two surface, and for a general capacitor, if it's of finite size, then there might be fields leaking from the sides. But what we are interested in is a really arbitrary capacitor that can be an arbitrary shape. And then my question is that what happens if we double this charge from Q to 2Q? So instead of this being Q, say this becomes 2Q. And my claim is that because of the superposition principle, the E field must also double, and the superposition principle also applies to the scalar potential V, and this makes the scalar potential double as well. And then we can define a quantity called capacity, that is Q over V, and that must be remains unchanged. But this argument might not be perfect in the sense that why can you guarantee that when in the processing of doubling the charge on a conductor, the conductor can have a surface charge distribution or a volume charge distribution, right? There might be a distribution of charge. So when you double this total charge, it's not guaranteed that the surface charge here will become a double here, right? It can rearrange itself to a slightly different pattern, right? And if that's the case, then we are screwed up. And really, it's not guaranteed that the V or the E field will be double. It can be a complicated problem and a different problem. And my claim here is that what happens in reality is that all this surface charge distribution simply become multiplied by a factor of 2, and we are saved from this disaster. And this capacity is really constant. And to see why, we have to go to the next chapter. So it's in chapter 3. Now, for example, if you can calculate the capacity of an ideal parallel plate capacitor, we've already seen this problem in the Physics 2041. So you can do the calculation by yourself. You simply find the E field, find the potential, and then if you divide the Q by the potential, that simply gives you the capacity. And in reality, for commercial product of capacitor, there will be materials fill in between this gap, because the epsilon naught of the vacuum is really small. And if you add a material, you can replace this a small number by a larger number. And we will discuss this in the chapter 4. So that's the chapter after 4 weeks. So now to summarize today's lecture, so we derive some of the equivalent potentials or equations for the scalar potential. So do you still remember the name of this potential, these equations? Like what's the equation for the scalar potential? So if you don't, then you need to look this up. So this is called for a general expression, it's called Poisson equation. And if the charge is 0, it's called Laplace equation. And then we also derived what's the E field and the B field should be on the boundary, say on the surface of a surface charge, or say on the surface of a conductor. And the third one is that we calculate the energy stored in the field. So for a given conductor, and if we fill this with a uniformly distributing charge, we know there is a E field, and simply integrating the E field square over the volume, that simply gives us the potential that is stored, potential energy stored in the field. And now last we learn a bit on the conductors, the capacitors, and the induced charge. So next week we will start to solve the Laplace equation and the Poisson equation, and that's the main topic of chapter 3. And there will be 4 lectures, and that correspond to 4 sections of the Griffins. So if you want to know what I want to discuss later, simply read the Griffins. I will exactly follow the order of Griffiths. And also, the homework 0 is due today, and I still see some of you haven't submitted the homework 0. And remember to submit the and sign the academic honest form. The homework 1 is already out, and it's due next Monday. There are 28 problems in that homework, so finish them early. And even though they are short, they still take time to finish, and you might get stuck after one of the problems. So try to discuss if you have problems in solving this homework 1.